Good day. Welcome to One-on-One Maths Private Tutors. We continue with Level IGCSE Physics on the chapter of waves, looking at the refraction of light waves. Let's start with definitions. Optical density is the ability of a material to transmit light through it. Light best travels or is fastest or travels freely in a vacuum. Light in a vacuum is fastest. Light in air is faster, almost the same as light in vacuum. Now, water and glass, light travels slower. Water and glass are optically denser than air and vacuum. So we can say light travels fastest in a vacuum and almost as much in air. In water and glass, light travels slower. A ray is a line drawn at right angles to a wavefront, which shows its direction of travel. Let's say we are generating waves in a ripple tank, for example. These waves are going out like that if we are starting from a point source. So the rays will be the direction of travel. So we can represent a wavefront by straight lines showing the direction. If we are generating straight waves by oscillating up and down, we generate straight waves like that. So the direction of travel of the wave is given by a straight line which is perpendicular to the waves. A ray is a line drawn at right angles to the wavefront, which shows the direction of travel of the wave. Refraction. Refraction is the bending of light when it passes from one material or medium to another. Let's say if light comes at an angle like this, incident light from air into glass. These are two different media. We have a normal like that. A normal is a line that is drawn perpendicular to the surface. This is our angle of incidence. So we have our normal and our incident ray. This is our angle of incidence, which we give I. And since glass is an optically denser medium, light will not continue in a straight direction like that, but it will be bended once it gets inside an optically denser medium. And we have an angle of refraction, which we term R. So we'll be looking at these properties. How is light bended when it passes from one medium to another? Facts about refraction. A ray of light is bent towards the normal when it enters an optically denser medium at an angle. So we can see the angle of refraction, which is this one, is smaller than the angle of incidence. So if these surfaces are parallel, this surface is parallel to that. When light leaves glass and enters into air, it will be bended again. The bending will be parallel to the incident ray. It regains its direction once again there. So we can see it enters at an angle of incidence. It is bended towards the normal. And when it leaves the glass, it is bended away from the normal at this position. So this is the normal at that position, 90 degrees here. And the direction is the same as this angle of incidence. So this will also be I, the same size of angle. That is, if these sides are parallel. A light ray is bent away from the normal when it enters an optically less dense medium. This is what we have been demonstrating here. So this is a denser medium, optically denser. This is a less dense medium. So light is refracted away from the normal. This is incident at this point, but we are coming from a denser to a less dense, so we bend it away. So know the two scenarios. When we are coming from a less dense to a denser, the ray is bended towards the normal. When we are coming from a denser medium to a less dense medium, it is bended away from the normal. A ray traveling along the normal direction at a boundary is not refracted. So if we have a ray and we have our normal there, we say this is our normal. If we have a ray traveling along the normal, or perpendicular to the surface, a wave is coming in there, it is not refracted, it is not bent, it goes straight through. Only waves that are coming in at an angle are refracted or bent. So a ray traveling along the normal direction at a boundary, at this boundary, this wave is not refracted, no bending, it goes straight through. Now, let's look at refraction in glass. What experiment could we do? This is the experiment we could set up. For this experiment, we require a lampstand with a shield so that light is restricted when coming out. We also require a single slit to allow a narrow beam of light out of the single slit. We also require a glass block and a sheet of paper, a pencil, and a protractor. We allow the light to pass through this single slit as a narrow beam. First, we need to trace our block A, B, C, D using a pencil. Allow a narrow beam of light at an angle towards our glass block. Then we mark positions of the path of the beam as it approaches our glass block. We also mark the entry point light into our glass block along AB, and we also mark the exit point of our beam of light along CD. We also mark positions of the light as it leaves CD. Next, we remove the block. What do we have? We have our piece of paper there, and we have our tracing of the glass block. So we have our markings, our tracing of our block A, B, C, D. Now we join the points we have constructed. Let's say this is the incident wave. This wave, we trace these points we have marked along up to the entry point. We also join the entry and exit point. We also trace the beam as it leaves CD. The next thing, we construct tangents at entry and exit point. Now we can measure the angle of incidence there, the angle of refraction. Since glass is optically denser than air, we find that the angle of incidence here is greater than the angle of refraction. And when the light leaves the glass, the angle of incidence from glass is less than the angle of refraction in air. And we will find that this line here, the incident beam, is parallel to the refracted beam in air. It will restore its direction once it goes past the glass. So in nature, where do we experience refraction? Let's look at this concept of real and apparent depth. When we are viewing objects underwater, let's say in a pool, they appear to be closer than they really are. An object at the bottom of the pool here will cast incident rays on the surface of the pool. These rays are refracted. So we have our normal there and our normal there. These waves are refracted with a higher angle of refraction since water is optically denser than air. So we have a larger refraction. Now, this angle of incidence is small. The angle of refraction will be small, this angle. So this incidence angle I1 will have a smaller refraction R1. Another ray of light will come at another point, and this is a larger angle of incidence. Let's call it I2. It will give an even larger angle of refraction, R2. The rays that come out from there are now diverging. Now we know rays form an image when they converge, when they come together. But in this instance, they are diverging. So to obtain an image, we would have to trace back these rays with virtual rays. These are virtual rays. The dotted rays are virtual. And where they meet, that's where the image is formed. So the image becomes a virtual image, virtual or apparent. Apparently, we can see the image is at a higher point than the object, so it appears shallow. Now, the real depth is greater than the apparent depth. We can also see this if a person is standing in a pool and we view at an angle, they appear to have shorter legs than they really have. It is all because of refraction of rays and the formation of a virtual image through virtual rays at a position that is higher than the actual depth. Another example is when you place a pencil in water and you observe at an angle. The pencil seems to bend at the water surface. So these are effects of the refraction. Now we go to refractive index. Light is refracted because its speed changes when it enters another medium. When you have glass and air. In an optically less dense medium, speed is high. In an optically denser medium, speed is low. So when a light wave enters an optically dense medium, its speed reduces. This causes it to be refracted towards the normal. This is the angle of incidence. This is the angle of refraction. Speed in air is approximately 3 times 10 to the power 8 meters per second. Speed in glass falls to 2 times 10 to the power 8 meters per second. So what happens is speed reduces and wavelength reduces. So there's long wavelength in air. Wavelength reduces and it's shorter in glass. What remains constant is the frequency. So from our equation of the wave V is equal to F lambda, we'll find that frequency is equal to V over lambda. Now to maintain a frequency, if this speed reduces when we are moving from a less dense medium to a denser medium, lambda, which is the wavelength, has also got to reduce in order to maintain a constant frequency. And also remember, when light leaves the medium, we have said it will be bended and it will be parallel to the incident ray. These two angles are equal. These two lines, this incident ray and this ray, when it comes out, will be parallel. That is if these lines are parallel. So when light is coming from an optically denser medium to a less dense medium, the speed increases and the wavelength increases so that it maintains the same frequency. So all the while when it gets into a denser medium and out of a denser medium, the frequency remains the same. The frequency does not change. Refractive index is defined as the ratio of the sine of the angle of incidence to the sine of angle of refraction. So let's N is equal to sine I over sine R. When we are coming from an optically less dense medium to an optically dense medium. Now, remember, when it's leaving the dense medium to the less dense medium, it's the reverse. So if this one is R and this one is I, it will be N is equal to sine I over sine R. Remember that I is now the angle of refraction and R is the angle of incidence. So it will be the reverse. Refractive index can also be the speed in air over the speed in glass. So it can be real depth over apparent depth, which is also equal to wavelength in air over wavelength in glass. All these are equations for the refractive index. Now, let's look at questions. The refractive index for a certain glass is 1.6, so we have n is equal to 1.6. Calculate the angle of refraction for an angle of incidence of 24. We have our glass there, our incident ray, our normal, our refracted ray. So our angle of incidence is 24. We want to find our angle of refraction. We know n is equal to sine I over sine r. We want to make r the subject of the formula, so sine r is equal to sine I over n. And we have r is equal to arc sine I over m. So r is equal to arc sine of sine 24, since our angle of incidence is 24, over n, which is our refractive index, 1.6. Using our calculator, go to shift arc sine, then fraction sine 24 over 1.6, and then you close our bracket, equals 14.7, which is equal to 14.7, which is equal to 15 degrees, since we are given our data in two significant figures. Let's look at this question. The refractive index of a certain glass is 1.5. N is 1.5. Calculate the angle of refraction for an angle of incidence of 30 degrees. Again, using the same principle, we have our angle of incidence, which is measured from the normal as 30 degrees. So we expect a refraction of less than 30. We know that N is equal to sine I over sine r. Sine r is equal to sine I over n. R is equal to arc sine of sine I over n. This will be arc sine of sine. Our incident ray is 30 degrees over our refractive index is 1.5. So this will give us, on our calculator, arc sine 30 over, close that bracket, over 1.5. Close that bracket outside there. Then we get 19.4, which is approximately 19 degrees, two significant figures. Now let's look at the concept of critical angle. When light passes at small angles of incidence from an optically dense to a less dense medium, such as from glass to air, there is a strong refracted ray and a weak reflected ray back into the denser medium, as well as some refraction. Some internal reflection occurs. Increasing the angle of incidence increases the angle of refraction. Okay, let's look at that scenario. So if we have our glass block and light is coming from the glass block, which is an optically denser medium, light is refracted away from the normal. If we keep increasing the angle of incidence, the angle of refraction will also become greater. If we keep increasing the angle of incidence, there will come such an angle of incidence I that the angle of refraction is 90 degrees. So we're coming from glass to air, and we know the angle of incidence here is less than the angle of refraction. So as we keep increasing the angle of incidence, the angle of refraction grows up to a certain angle of incidence, which will cause the angle of refraction to be 90 degrees. Now, such an angle of incidence is called the critical angle. Okay, so we can define critical angle as the angle of incidence from an optically dense medium to an optically less dense medium, which results in an angle of refraction of 90 degrees. If we are coming from a denser medium to a less dense medium, we say N is equal to sine R over sine I. Remember, it's the reverse when you are coming from a less dense to a denser medium. We say sine incident over sine refracted. But when you are coming from a denser medium, we say sine of refracted over sine incident. So at critical angle, R is equal to 90, N is equal to sine 90 over sine C. From calculating, we know sine 90 is 1. If we say sine 90, get 1. Refractive index of a material can be found by saying 1 over sine C, since sine 90 is 1. Now, if we go beyond the critical angle, our wave is reflected back totally. Our angle of incidence will be equal to our angle of reflection from the laws of reflection. Incident will be equal to reflection, and our ray is reflected back totally. So we have total internal reflection. This occurs when rays of light do not cross the boundary between two media and is reflected back when the angle of incidence is greater than the critical angle. Okay, that is total internal reflection. Now let's look at an example. If the critical angle for diamond is 24 degrees, calculate its refractive index. So if we have diamond and we have its critical angle is 24 degrees, we want to see its refractive index. We know refractive index N is equal to 1 over sine C, which is 1 over sine 24, which is 1 over sine 24, which is 2.5. Now let's look at this question. Fig 7.1 shows a ray of light. The ray passes into a semicircular block of glass at A and leaves the glass at B, traveling along the surface to C. State the name given to the angle of incidence marked as 40 degrees. We can see that the ray has been refracted at 90 degrees to the normal along this flat surface, so this angle is called the critical angle. Calculate the refractive index of the glass. The refractive index N is equal to sine of the refracted angle, which is sine 90 over sine incident angle C. So we use this method when we are traveling from a denser medium to a less dense medium, from glass to air. But we know sine 90 is 1, so it's 1 over sine C, which is 1 over sine 40. C is the critical angle. This will give us 1.6 to 1 decimal place. And the refractive index is a number with no units. So our refractive index is 1.6. A ray of light is incident on a plastic block in A. So this is A, this is the plastic block, at an angle of incidence I. The refractive index of the plastic is N. The light ray refracts along the plastic air boundary when it reaches X. So 49 is our critical angle, since the light refracts parallel to the surface. Which equation is correct? let's form equations that make sense here. The refractive index of the glass N is equal to sine I over sine 41. And for this situation, we know that the refractive index N is equal to 1 over sine 49 from 1 over sine C. Since 49 is our critical angle, so we want an equation that can be rearranged to either one of these forms. Sine I is equal to sine 41 over N. So if we make N the subject of the formula here, N is equal to sine 41 over sine I, which is not the same as this, so this is incorrect. Sine I is equal to N over sine 49. There's no relationship between I and 49. I is only related to 41. Sine I is equal to N times sine 41, making N the subject of the formula here. You can say N is equal to sine I over sine 41, which is the same as this, so this statement is correct. Again here, I and 49 don't have a relationship. I has only a relationship with 41. So our answer is C. Now let's look here. A ray of light passes into a block of transparent material as shown. What is the refractive index of the transparent material? Now in this question, we have to draw a normal there and then calculate the angle of incidence, which is this one, which is 90 minus 35, which will give us 55 degrees. So this is 55 degrees. And there the angle of refraction is 90 minus 60, which is 30 degrees. Now refractive index N is equal to sine I over sine R, which is sine 55 over sine 30, which is 1.64, which is C. So with that, we come to the end of this section. Thank you.